Good day. Our chat session today is about the topics our Hindu-Arabic system and early positional systems. This is dealing with, in our textbook, Chapter 4. First of all, the word number refers to describing how many, whereas the numeral is a symbol used to represent a number. For example, the capital X means 10 in the Roman numeral system. So that is a symbol that represents a number. A system of numeration consists of a set of basic numerals and rules for combining them to represent numbers. The Hindu-Arabic system this is the system we presently use, and its digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Remember, in our Hindu-Arabic system, we have something that are called exponents. So if we have something like b raised to the n, the b is considered our base, and the n would be the exponent or power. For example, 4 with an exponent of 2 means 4 times 4, because 4 is written down 2 times and multiplied. Now, expanded form, which is a concept your textbook talks about, uses exponents. So when we're told to write it in expanded form, for example, the number 237 would be 2 times 10 raised to the second power. The caret symbol means the number after it is an exponent, plus 3 times 10 raised to the first power, plus we would write 7 times 1. That's an example of expanded form. The Hindu-Arabic system is called a positional system or place value system. Positional values in the system are based on powers of 10. So like 10 to the 4th, 10 to the 3rd, 10 to the 2nd. Now the Babylonian system, another system discussed in chapter 4, goes back from 2000 BC to 600 BC. And its symbols the V, lowercase v, for 1, and something that looks like our less than symbol stands for 10. The place values in the Babylonian system are powers of 60. So place values for the Babylonian system start off and then 1. Now, let's take a look at a symbol of a number in the Babylonian system. Suppose we have the following symbols. This would be 1 times 60 raised to the second power plus 10 times 60 raised to the first power plus 1 plus 1 times 1, which names the number 4,202 in our system. A major disadvantage of the Babylonian system is that it did not have a symbol for 0. Some Babylonian tablets have a larger gap between the numerals or the insertion of the two symbols that look like less than to indicate a missing place value. Now let's go on and talk about the Mayan numeration system. Now, the Mayan numeration system was created by the Maya, a tribe of the Central American Indians, lived in the Yucatan Peninsula, developed in this system between 300 and 1000 AD. And I'm going to recommend that you go into chapter 4 and look at the symbols for the Mayan numeration system. Now, it is based on the number 360, which was the number of days in one calendar year for the Mayan calendar. The numerals in the Mayan system are written vertically. Now, let's go into number bases and positional systems. Okay, now, recall base 10. When we talk about place values in base 10, we have 10 raised to the 4th, 10 raised to the 3rd, 10 raised to the 2nd, 10 raised to the 1st, 10 raised to the 0. Those are our place values in our base 10 system. Well, we mimic what we just did here for other bases. So let's take a look at, for example, base 2. For example, base 2 would have 2 raised to the 4th, 2 raised to the 3rd, 2 raised to the 2nd, 2 raised to the 1st, 2 raised to the 0. 8, 4, 2, and 1 are the first place values in base 2 system. So if we write 101, base 2, base 10 is the only base where you will not see a subscript word written to tell you the name of the base. Now, this is not read as 101 base 2. This is read as 101 base 2. We read the digits, but we do not read it in terms of base 10. This means that we have 1 times 2 to the second plus 0 times 2 to the first plus 1 times 2 to the 0, which would equal 4 plus 0 plus 1, or the number 5 in base 10. So recalculating 101 base 2 into base 10, it would name the number 5. Now, changing to base 10. Okay, changing to base 10. To change a numeral in a base other than 10 to a base 10 numeral, first, find the place value for each digit in the numeral. Multiply each digit in the numeral by its respective place value. Find the sum of the products in step 2. Now, computers also use base 2 and base 8. Base 8 is called an octal system. And they sometimes also use base 16. Now, suppose you are changing from base 10 to another base. Find the place values for the new base. Find the place values less than the original base 10 numeral. Express the number as a group. So, for example, 7 would be equal to 2, 1, base 3. of computation in positional systems. Okay, you have two options. You can first convert each number first to a number in base 10, or do the operation within the given base. Let's take a look at an example. Suppose you have 2 base 4 added to 1 3 base 4. This would become 1 0 1 base 4, because 2 plus 3 would be 5, but 5 is 1 in base 4, so we would write down the 1 and we would carry the 1. And then 1 plus 2 plus 1 is 4, which is 1 0 in base 4. Or what we could do is 2 base 4 is going to give us 10, and then 1 3 base 4 gives us 7, and if we add those together, 10 plus 7 gives us 17 in base 10. So this would be doing the problem in base 10, where the problem on the right is doing it, keeping it in base 4, because 1 0 1 base 4 is the same as 17 in base 10. Whereas if we do subtraction, suppose we have 2 1 base 4, and we are subtracting 1 3 base 4. This would give us 2 base 4. Because 3 from 1 we couldn't do, so we'd have to borrow. And since we can't subtract 3 from 1, we borrow 1 from the preceding problem. We are working in base 4, so we are borrowing one group of 4. So 4 plus 1 actually gives us 5, and 5, take away 3, leaves us with the 2. And we've already borrowed 1 from the 2, so 1 minus 1 is 0. So all we're left with is 2 base 4. Now if we convert it to base 10, this would be 9 subtract 7, which also gives us 2, and that's in base 10. So we could either do the problem in base 10, or we could do the problem in base 4. Now, let's take a look at multiplication. Suppose we have 1 2 base 4 times 3 base 4. This would give us 102 base 4. 3 times 2 gives us 6, but 6 is not a digit in base 4. So we convert 6 to its numerals in base 4, 1, 2. Hence, we write down the 2 and carry the 1. 3 times 1 is 3, plus the 1 is 4. 4 is not a digit in base 4, so this becomes 1, 0 in base 4. Hence, the answer is 102, base 4. I recommend on the division that you review your textbook because you need to refer to the multiplication chart that is given there. Now, let's look back at some early numeration systems. Okay, first of all, we'll look at the Egyptian numeration system. This is the oldest Egyptian numeration system was developed around 3400 BC. And I recommend that you review your textbook for the exact symbols. Now, okay, each of the symbols in the Egyptian numeration system have names for them, like lotus blossom and pointing finger and tadpole and astonished person. And it takes far more space to write their numbers than it does our own in the Hindu Arabic system. It is an example of an additive system, whereas we can sum up the digits that are drawn to get the value of the number. Now, another common early numeration system, which we still use for outlining in some textbooks, is the Roman numerals system. Now, it's also sometimes used for clocks. The numerals come from letters in the alphabet. And here they are, I, B, X, L, C, D, and M. Those are the symbols in the Roman numeral system. If the symbols decrease in value from left to right, then we add their values. But if the values increase in value from left to right, then we subtract their values. For an example, x11 equals 10 plus 1 plus 1, which equals 12. But if we have I and then V, this is 5, subtract 1, which is 4. So in one case, we had the numbers increasing in value. In another case, we had decreasing in value. Now, we also have a system called the traditional Chinese system. In the traditional Chinese system, it is missing a symbol for 0. And the symbols are written vertically. Again, I urge you to review your textbook for the different symbols that they use in the Chinese numeration system. Our next one that we're going to talk about is the Ionic Greek numeration system. The ancient Greeks, masters of art, architecture, theater, literature, philosophy, geometry, and logic, were not masters when it came to representing numbers. Their system goes back to 400 BC. 150 BC. Again, I urge you to go in your textbook, see page 219 for their symbols. And to represent a number from 1 to 999, the appropriate symbols are written next to one another. So symbols are written next to one another. The plus sign is left out. This concludes our first lesson. I hope that you found it helpful. Please don't hesitate to contact me if I can help you in any way. I'll be glad to assist you. Thank you for listening to this lesson.